Open Cloudflare's traffic chart, and you'll find a number that surprises people. About a third of all web traffic now runs over a transport protocol that did not exist a decade ago. Not over TCP, over UDP. The browser, the data center, every middlebox in between, they collectively rewrote the most foundational layer of the internet, and almost no one outside the protocol world noticed. The new transport is called QUIC. The application layer that rides on top of it is called HTTP3. Cloudflare serves it. Google serves it. YouTube, Instagram, and Meta all serve it. Your browser already speaks it by default whenever the server offers. This is one of the strangest deployments in networking history. The pipes look the same. Your URL bar still says HTTPS, but underneath, the transport got rewritten, built on UDP, assembled in user space, and encrypted to the bone. So today, we look at why. To see why QUIC exists, look at what HTTP2 over TCP gets wrong. HTTP2 multiplexes. A single TCP connection carries many parallel streams, your HTML on stream A, a style sheet on stream B, an image on stream C. From the application's point of view, the streams are independent. But TCP doesn't know that. TCP sees one ordered byte stream. It promises to deliver every byte in order, exactly once. The kernel cannot tell stream A's bytes apart from stream B's. So when a single packet gets dropped, say, a packet belonging to stream A, TCP holds back every byte that arrived after it. Stream B and stream C are ready, sitting in the receive buffer. The application can't see them. They're stalled, waiting for stream A's retransmit. One drop, 3 stalls. This is head-of-line blocking, and it happens every time you load a page over a flaky link. The fix is not at the application layer. It has to be at the transport layer, and TCP cannot get there from here. So why not just fix TCP, add a feature, ship it, done? The reason is a phenomenon called protocol ossification. Between your laptop and any server, packets pass through a parade of middleboxes: your home router, your ISP's NAT, corporate firewalls, CDN load balancers, deep packet inspectors. They were built years or decades ago. They learned what a TCP packet should look like, and they enforce it bit for bit. Try to add a new TCP option. A meaningful fraction of paths, somewhere between 5 and 15%, will silently strip it, mangle it, or drop the whole packet outright. Your new feature works in a lab and dies in the wild. Linux ships TCP improvements every release. Most of them stay disabled in production because the operators have learned. Anything non-vanilla breaks somewhere, and you can't tell where until users complain. TCP isn't broken because of its design. TCP is broken because it cannot change. The protocol is frozen in amber, watched by 1,000 middleboxes, and there is no version 2. So if you cannot evolve TCP, what's left? You go around it. UDP is the other transport protocol. It's simple, a thin envelope, no handshake, no reliability, no ordering. Middleboxes have always passed UDP traffic, mostly because DNS, video calls, and games depend on it. They don't try to inspect UDP payloads the way they inspect TCP. UDP is the one substrate the internet still passes through cleanly. QUIC's move is to skip TCP entirely and rebuild reliable transport on top of UDP, in user space, inside the browser and the server. Look at the new stack. UDP at the bottom. Above it, a single fat layer called QUIC that absorbs 3 things at once: transport, reliability, encryption, and stream multiplexing. Above that, HTTP3. Above that, your application. The kernel only sees UDP packets going in and out. It has no idea anything more sophisticated is happening. The middleboxes have no idea either. Everything that used to live in the kernel and the middlebox now lives in the application, where it can actually evolve. Once you control the whole transport, you start fixing things. The first thing QUIC fixes is the handshake. A fresh HTTPS connection takes 2 round trips before your first byte of real data leaves your laptop. The TCP 3-way handshake costs 1. Then TLS 1.3 costs another. The client sends its hello with a key share. The The server replies with its own key share and a certificate, and now both sides have a shared secret. After all that, your browser can finally send the actual HTTP request. QUIC folds the transport handshake and the TLS handshake into a single exchange. The first packet your client sends carries the transport parameters and the TLS client hello together. The server replies in one go. After exactly one round trip, the connection is open and encrypted, and the next packet is your HTTP request. For repeat visits, it gets even better. The client caches the server's keys. Next time, it sends application data in the very first packet, 0 round trips before data flows. On a 60-millisecond link, that saves 60 to 120 milliseconds before the page can start to load. Now back to the head-of-line problem. QUIC's fix is to make streams a first-class concept inside the transport itself. In TCP, the kernel sees one byte stream. In QUIC, every UDP packet carries one or more frames, and every frame is tagged with a stream ID and an offset. Stream A and Stream B are not interleaved bytes. They are separately tagged, separately tracked, separately recovered. So watch what happens when a packet gets lost. Stream A's lost packet has to be retransmitted, and Stream A's receiver waits for it. But Stream B's packets and Stream C's packets keep arriving. They have their own ordering. Their bytes go to the application immediately. One drop blocks one stream, the other streams keep flowing. That's the problem from Scene 2 solved at the right layer, at the transport, where the protocol can finally see what TCP never could. It's a small idea, but it's the thing that lets a web page with 200 small assets load over a single connection without one slow asset poisoning all the others. Here's a problem that was always painful with TCP. You're on a video call, walking out of the coffee shop. Your phone drops Wi-Fi and switches to cellular. Your IP address changes. A TCP connection is identified by a 4-tuple source IP, source port, destination IP, destination port. Change any one of those, and TCP sees a different connection. The old one looks dead to the server. Your call drops, and the app has to reconnect from scratch. QUIC identifies connections differently. Every QUIC connection has a connection ID, a short random identifier that both sides agreed on during the handshake. The connection is the ID, not the addresses. So when your phone switches networks, the new packets arrive at the server with a fresh source IP and port, but they carry the same connection ID. The server recognizes you instantly, validates the new path, and resumes the connection where it left off. The video call doesn't drop. This is the unsung benefit. On a phone that walks between networks 5 times an hour, QUIC just works. QUIC encrypts more than its payload. It encrypts most of its own header. In a TCP packet, you can read the source and destination ports, the sequence number, the flags, the window size, and the TLS record headers all in the clear. Middleboxes love this. They learn to depend on it. They build features that read those fields. And once they depend on those fields, the protocol cannot change them. That's the ossification trap from Scene 3. A QUIC packet exposes only a tiny clear header, the connection ID, and a couple of flag bits. The packet number, the stream framing, the version negotiation, the congestion signals, all encrypted. A middlebox holding a magnifying glass over a QUIC packet sees almost nothing it can act on. This is not just a privacy story. Encryption is also armor against ossification. If middleboxes cannot peek, they cannot calcify the protocol around their assumptions. The header becomes opaque on purpose, so the next version of QUIC is free to change everything inside it. TCP's mistake was being readable. QUIC will not make that mistake again. There's one more change worth understanding, and it's the deepest one. QUIC moved transport into user space. That changes how fast the transport can evolve. Look at TCP's evolution. The QUIC congestion controller, default on Linux, dates from 2006. Google's BBR was published in 2016 and only landed in mainline Linux a year later. BBR version 2 appeared in 2019. BBR 3 in 2023. Each step took years to merge into the kernel, then years more for distros to ship it, then more time still for cautious operators to enable it. Now look at QUIC. Cloudflare and Google ship congestion control changes, loss recovery tweaks, pacing improvements, MTU probing experiments every quarter or two. They go out with the next browser update. Server-side improvements ride the next deploy. The kernel didn't get faster, the protocol moved out of it. This is the change with the longest tail. The cadence of transport evolution went from years per change to weeks per change. Whatever transport innovations come next will arrive over QUIC, not TCP. So that's QUIC, and that's where it lives now. Cloudflare reports about 30% of all the requests it sees use HTTP3. Google has defaulted its properties to QUIC since 2020. Every search, every YouTube view, almost every Google API call. Meta serves Instagram Reels and a large slice of Facebook video over QUIC. The 5 things QUIC changed are worth remembering. 1 round-trip handshake, independent streams that don't block each other, connection IDs that survive a network change, encrypted headers that resist middlebox ossification, and a transport that ships with the next browser update, not the next kernel. QUIC didn't add a feature to the web. It moved the transport layer out of the kernel, and that one move enabled all the rest. Next time you load a page over HTTPS, check the Protocol tab in your browser's DevTools. There's a fair chance you're already running on UDP and you didn't even know it. Thanks for watching.